Hello everyone, I hope you are all doing well. If we monitor our Java application's memory footprint, we may observe that 25 to 30% of memory consumed is due to string objects. In some large applications, this percentage can be even higher. We all know that to reduce memory wastage due to string objects, the JVM uses a technique called string interning, also known as the string constant pool, to reuse string literals. Since we frequently interact with string literals in our Java applications, each interaction involves native code. This is because the string pool in Java is implemented natively. Interacting with the native part of the application involves some overhead due to the context switching, GNI involvement, bypassing JVM optimization, memory management by the native code, and dependency of the native code on hardware and operating system. So in today's adventurous journey through the land of strings, we'll explore the internal working of string interning and discover how to optimize string pool latency and reduce the memory footprint of our Java applications due to string objects. As you all already know, this is a famous interview question and a topic of much discussion. How many objects are created, what their memory locations are, and when they are created, as well as question related to equals and equals method. While we won't focus on the true false outcomes of these comparisons, we are all familiar with string literals, string pool, and string interning, and we likely know the output of these statements. There is still an area of uncertainty due to the lack of clarity about when a string will be interned and the inability to directly access the string pool. These questions remain popular and continue to be debated. Suppose we have a string s and we want to determine whether this string is in the pool. The only way to verify this is by using s equals to s dot intern using intern method. If this expression returned true, it means the string is already in the pool. Otherwise, this will add it to the pool. By the end of this discussion, we'll have a clear understanding of when strings are interned and when they are not, supported by proof and examples. Let's start with some theory when strings are interned and when they are not. The first one is, I trust you all know this. When we create a string using string literal, it is always interned by the JVM. The second one, when we create a string using new keyword, it will always create a new string inside the heap. The first point of confusion is whether the constructor argument will be added to the string pool or not. The answer is that this literal constructor argument will be added by the JVM to the string pool if it doesn't exist already. And the third one, the second point of confusion is whether strings created from external sources will be added to the string pool or not. The answer is when creating a string from external sources like reading string from files, network, user input, or creating dynamically, the strings are not automatically interned. We must explicitly use the intern method if we want to add them to the string pool. So there is one question from my side. Why are strings not automatically interned when they are created from external sources or dynamically? Now let's validate all these statements with proof. To validate, we will be using JCMD utility. The JCMD utility is used to send diagnostic command request to the JVM. In our discussion, we will be using vm.stringtable command. So the commands are as follows: JCMD, process ID, and vm.stringtable. It will show the string pool statistics, and if we will provide verbose option, it will dump the whole string table, string pool. So we will use two commands, this one and this one. Let's check the output we get from these commands. First, we'll list out all the JVM processes running in this machine. So we'll use JPS command for this. This is also a Java utility. So let's see what will be the output for process ID 6892. 6892. So this is the string table statistics, number of buckets, number of entries, number of literals, total footprint, average bucket size, variance, standard deviation, and maximum bucket size. Let's see the output of with verbose. This is the output of verbose option, but we'll use only this command to verify what we have discussed so far. We'll use process ID, verbose, and grab the particular literal. We can also use the JVM flag print string table statistics to obtain similar information as the vm.stringtable command. However, this flag will print the statistics when the JVM terminates rather than during runtime. In the JDK implementation, the string pool is called the string table and it is backed by concurrent hash table from Java 11, and previous to this it was backed by hash table. This is the implementation of JDK string table. I will share this link with you. You can explore this one. Let's execute some code. This is our test class which we'll use to validate everything we have discussed so far. To verify, we'll debug all the methods and run the jcmd command to observe the string table statistics both before and after creating the string literals. To validate everything, I will use vmstring verbose command and filter the results to search for specific literals. If we find the literals in the output, it means it is present in the string pool. I have created a class StringIntern Diagnostic to access the jcmd utility, which you can use for the same purpose. I will provide links to the resources and GitHub repository so you can review them. Let's start with this method. So this is a class. What do you think when the class loader loads this class into memory, how many string literals from all these variables will be pulled? So we are loading this class using class.forName and we'll debug at this point. So at this point, this class will be loaded into memory. So let's see, before creating a new instance, how many string literals will be pulled. Let's see. So this is the process ID. Let's execute this command. We can observe that only static field literals are pulled initially. This is because during the class loading preparation phase, static fields are created and initialized with default values. These static fields are then assigned their actual values and any static block are executed during the initialization phase. Now let's see, when this statement is executed, how many new string literals will be pulled. We are creating the new instance from this class. Now let's see again. Now we can see all literals are pulled. So after creating an instance of this class, all fields are pulled. This happens because we know instance field only come into existence when an instance of the class is created. The reason I showed this example is to address a common misconception that all string literals are pulled during class loading. This is not true. Only static string fields are pulled at class loading. Instance string fields are pulled after the object is created, and local string literals are pulled when the method's bytecode is executed. You can test both these methods using the same approach. For this one, at this line, there is no string inside string pool with name local string. After this line is executed, this literal will be interned. Same for this. At this line, there is no string inside the heap or string pool. After this line is executed, the one object is created inside heap and the literal J for Java will be added by the JVM to the string pool if it does not exist already. So you can test both. Let's verify for random strings. Let's debug it. A random string is created with 2701. Let's check it. The process ID is 8484. So currently no string literal inside string pool. Now let's call the string.intern method, which will intern this string inside string pool. Let's check again this command. Now we can see the string literal is interned. You can check this one. When we add a variable with a string literal, it becomes a runtime string. So the first statement will return false, and when we intern it, then it will return the reference from this string. So it will become true. The same way we can test strings coming from file or network. At this line, this string will not intern by default. When we call string.intern, only then it will be interned. Let's see how we can improve the string table latency by analyzing the output from the JCMD utility. The string table statistics such as average bucket size, variance of bucket size, and standard deviation of bucket size can be used to monitor and optimize this. A low average bucket size indicates better distribution of keys across buckets. Variance and standard deviation help identify how evenly the keys are spread. Higher values suggest more imbalance. If we notice the average bucket size or variance values increasing due to collision, which may result in higher latency in string table operations, we can consider increasing the table size by using the JVM flag when running our application. So we can use this JVM flag, string table size and any value. In Java 12 and later the default string pool size is 65,536. So friends, I have one more question for you all. The question is, why is the string pool implemented natively rather than in Java? Now let's see how we can reduce the memory footprint of our string objects in our Java application. As we know, the string pool is memory optimization technique used to reduce the memory footprint of our string literals. But what about string created at runtime from external sources? These can create duplicate string in the heap. For example, the keys in the request and the column name in the database responses are same. Each time they are deserialized, duplicate string are created in the heap. To optimize these duplicate string, a JVM flag was introduced in Java 7. Use string duplication. This flag enables string duplication. By default, this option is disabled. To use this option, we should switch to G1 garbage collection if our application is currently using a different GC. String duplication reduces the memory footprint of string objects on the Java heap by taking advantage of fact that many string objects are identical and immutable. Instead of each string object pointing to its own character array or byte array from Java 9, identical string objects can point to and share the same character array. In this way, we can potentially reduce the memory uses of string objects. And the last one, by using compact string. So starting with Java 9, Java uses byte array instead of character array. So previously, the string is implemented as character array. But from Java 9, this is replaced by byte array, and also introduces the JVM flag compact string, which is enabled by default. Previously, each character requires 2 bytes to represent a single character. Now it uses a single byte per character with ISO 8859 Latin 1 encoding. For any multi-byte character, these are represented and stored using 2 bytes per character with UTF-16 encoding. This approach can potentially reduce the memory uses of string objects by 50%. However, you should disable this option only if your application primarily deals with multi-byte character UTF-16 strings. Otherwise, don't touch this in production. So friends, that's all for today's exploration of string pool. I hope you enjoyed the video and now have a clearer understanding of it. Thank you for your time and attention. See you soon. Until then, keep learning and take care. And finally, I will leave you with this thought. Let this inspire you to make a positive impact.